In this video, we continue with goodness of fit tests, and we specifically look at composite hypotheses. When we have a random variable and we want to do a goodness of fit test to see whether the random variable follows some specific discrete or some specific continuous distribution, we considered the case where the parameters were known in the previous lecture. In this one, we're going to look at the situation where the parameters are unknown and need to be estimated, and where the null hypothesis is a function only of these parameters. But I'll explain with an example and the theory later on. For this section, please note that you should use the slides and not the textbook. In the textbook, a method of maximum likelihood is used, which we haven't discussed, and it may confuse you. So the study material in these slides are sufficient for this section. We're still in the theoretical scenario of a multinomial experiment, where we observe counts in k categories, and we have a model which specifies what the probabilities in each category is. Now, the model may be some distribution which determines these probabilities. Now, given the probabilities that can be calculated from our model or our null hypothesis, we can determine the expected frequencies, and we can then compare that to the observed frequencies, which yield our chi-square test statistic, which compares observed and expected frequencies, square them and divide by the expected frequency. Then we know that we have a chi-square test statistic with k minus 1 degrees of freedom. That is provided that all the expected frequencies in each category is at least 5. If that's not met, you have to reduce the number of categories by combining adjacent categories. So this is the general layout, and you're going to use this still for this section and for this whole chapter. All that's different in this section, I'm going to illustrate first with an example and then the theory. So with the example, to illustrate the difference, here you have the same on the left-hand side, the same layout, and what you've done before is the situation where lambda is known, and now lambda is unknown. Now, what is lambda? Lambda is the expected value of a Poisson. Sorry, I neglected to say we're considering specifically a Poisson distributed random variable, or we want to test whether a specific random variable has a Poisson distribution. But now lambda is unknown. Now remember, lambda is the expected value of y. And the expected value of y can be denoted by mu, the average of the distribution, where it is centered. So if we want to estimate lambda, we can do it by estimating the expected value. And the expected value is given by, that is just the average of a group data set. But I'll get back to that later on. So we're simply going to get the average, calculate the average from the data given, and then we're going to use that to estimate lambda, and then we can calculate our estimated probabilities under the null hypothesis using lambda hat. So that's the only difference between what you have when lambda is known and lambda is unknown. Here you have lambda hat to the power y e to the minus lambda hat divided by y factorial. What is y again? Y is the values that are associated with the different categories. A value of y being equal to 0. In other words, remember what is our random variable for a Poisson distribution? The number of times that something occurs, and it can be 0, up 1, up to infinity for the Poisson. And the fact that it goes up to infinity is also something that we need to take care of, but I'll get to that later on. The point is, What differs between the two sections is that now you estimate lambda and this. Your degrees of freedom when lambda is known is k minus 1 number of categories with at least 5 expected frequency of at least 5 in each category. If we assume that the same assumption holds in both cases, then where lambda is estimated, we lose another degree of freedom. Remember, the degrees of freedom are the number of independent categories. But because we know the total number of observations, we know that all the probabilities add up to 1. We know that the last probability will be determined by the first k minus 1 probabilities. So therefore, the degrees of freedom for the chi-square test is k minus 1. But now when you estimate a parameter, you use another degree of freedom, so that's k minus 1 minus 1. So let's look at the theory. In your textbook, you can have a look at this paragraph because it's quite important and explains the concept well. When we have a situation where we have k natural occurring categories, but the null hypothesis states that only that the probabilities are functions of other parameters. Now, this may be only one parameter or more parameters, but without specifying the values of these parameters. Then we call this a composite hypothesis, because the hypothesis is going to be such that the null hypothesis, when it is true, does not uniquely determine the cell probabilities or the expected cell counts, but only their general form. So you first have to estimate your theta. Now you have an example here in the middle that is an example from genetics, where they look at 3 genotypes, so that's your 3 categories, and they have a hypothesis that the probability that you get the first genotype, which is double capital letter A, the probability of that occurring is a function of a parameter theta, where theta represents a proportion of gene A in the population. But that probability now is theta squared. And in the second probability, that is the occurrence of the second genotype, is 2 times the same parameter theta times 1 minus theta. And the third probability is 1 minus theta squared. So you can see what's important here is the pattern that you have in the probabilities and not specifically the value. So that is then what we're going to use in this section. And the examples, for example, we are interested in whether a sample came from a particular family of distributions without specifying any particular member of the family. So you just want to know whether the data you have can be assumed to come from a Poisson distribution or a normal distribution, but without specifying specific parameters. For the Poisson, we needed to estimate lambda, and if you have, for example, a normal distribution, you will have to estimate mu and sigma, the 2 parameters there. So the theory and the examples from the bottom of page 732 to 741 are excluded. Replace these examples with the examples and the additional material in these slides, please. Okay, in this section then, I'm going to consider examples based on the following distributions and therefore recall the probability mass function of the Poisson, the binomial, and the probability density function of the normal, and also recall the expected value for each of these distributions, namely lambda, n times p, and mu. So I'm going to do the first example thoroughly, but you will see that the procedure remains the same. So I will, for the second and third example, then just explain or point out things that may cause difficulty. Alright, chi-square when parameters are estimated. Before I start with my first example, I am going to just look at the theorem that's given in your notes. Now I've already said we have to estimate parameters theta 1 to theta m. And probabilities associated with these parameters. The theta here, let me just explain quickly, is a vector. So theta is written as a column vector, theta 1, theta 2, up to theta m. And so there's certain probabilities associated with each parameter. But look at the test statistic that's given there. Observed minus estimated expected. And that's the only difference between what you've had and what we have now. We have the observed frequencies minus the estimated expected frequencies squared divided by the expected frequencies. Don't let this notation confuse you. It's simply the estimated expected frequencies because you have the expected frequency, which is also always n, your grand total, times the probability of a specific category. And we can also write this as the notation that I used earlier is this is actually p hat I under the null hypothesis. That's this pi I, theta hat is the same as pi hat I under the null hypothesis. It's just other notation to imply that we're working with a composite hypothesis. But note that nothing has changed. The chi-square test statistic is calculated in the same way. We are saying that these parameters are being estimated by the method of maximum likelihood, as described previously, but we did not do that. So don't worry about the method of maximum likelihood. It's just a method of estimation. And the method of estimation that we are going to teach you yield maximum likelihood estimators, but that's not relevant now. You just need to know how to estimate parameters, and we'll show you how to estimate these parameters theta 1 to theta m. So that's the first thing, the estimation of the parameters. And the second thing is this test statistic now has a chi-square distribution, but with a change to the degrees of freedom, namely k minus 1 minus m. Note that we estimate in general m such parameters, and therefore we subtract m degrees of freedom. But mostly in the examples that we will be considering, m will be only 1 or 2. Still, the requirement is also that your degrees of freedom in each cell should be at least 5. All right, so there's the two important things that, or the one important thing that you have to remember regarding the distribution of the test statistic after you've calculated the parameters. So there's the two changes in this section. And now I'll get to the examples. In the first example, I consider exercise 12 in your textbooks. The question is, are the frequencies from a binomial distribution? What are the frequencies? Consider a large population of families in which each family has exactly 3 children. So it's 3 children families. If the genders of the 3 children in any family are assumed to be independent of one another, the number of male children in a randomly selected family will have a binomial distribution based on 3 trials. Because each family, they can have 0 boys, 1 boy, 2 boys, or 3 boys. So the number of male children for 160 such families were recorded and yielded this frequency distribution here. So now you have to be careful. We have a binomial distribution and we have a repetition of a binomial experiment. The binomial experiment has parameters n and p. And in this case, this binomial experiment of us has n equal to 3 and the probability of 0, 1, 2, and 3 children are unknown, and that's what we want to determine. But note that we repeat this experiment 160 times. So generally we use n for the parameter for the binomial and n for the total number of frequencies. So don't confuse them. They are two separate things. You have to clearly distinguish between the two. Point is, first thing that we need to do is we have to estimate p hat. How are we going to estimate p hat? Now, the mean or the expected value for the binomial distribution can be calculated by the so-called grouped mean. In other words, for this data, we can calculate a mean in the following manner. We just weigh each value, 0 with 14, 1 with 66, 2 with 64, 3 by 16. And this is the general formula that I indicated earlier. 1 over n, each x value weighed by its frequency. And you get a mu hat, an average number of male children of 1.5125. But how can that help us to estimate p for the binomial? Now remember that the binomial has parameter n equal to 3 and p is the unknown. But what is mu for the binomial? It's n times p. So because mu is n times p, we can use the fact that p is equal to mu divided by n. So that's our estimate of the parameter p, 0.504. P is equal to mu divided by n, and therefore we can say p hat is divided by mu hat over n. And now we do the same as what I've indicated briefly using the Poisson example. There's our table that we always need for calculation. Now the first thing we need to do is determine the probabilities under the null hypothesis. That's determined by the binomial distribution. And the binomial distribution has parameters n and p. And now we've estimated p. And we can just substitute into the formula for the probability mass function. We can substitute p by p hat. So you will note there's my p hat and 1 minus p hat. Don't let my notation confuse you. I'm referring to category I, but category I is associated with certain values of x, 0, 1, 2, 3, 4. So you can see x is equal to I minus 1, and that's why I use I minus 1 here. This is basically x, n combination x, p to the x, q to the n minus x, n minus x. It's the same, it's just because we have to take into account how many categories there are, and we also have to take into account the different values that the random variable can assume. All right, so given that, I can substitute my I in here and I can calculate my probabilities. There's my theoretical probabilities coming from the binomial distribution, because that is our null, it's going to be our null hypothesis that it is binomially distributed. Now we can just multiply by the grand total, namely there were 160 families considered, and therefore our expected frequencies are given in this column. Please work accurately enough so that you have your totals being equal. And now you can get your cell chi-square values by comparing your observed frequency to your estimated expected frequency. And there you have them. All the expected frequencies are larger than 5, so you can just work with these 4 classes. There's your final chi-square value, and now you can proceed with your test. Again, do not confuse the parameter of the binomial distribution. Remember, the binomial distribution has 2 parameters. So in our general theory, that would be a parameter theta 1 and a theta 2. In other words, m equal to 2. I'm referring to the previous slide where we looked at the theory. So theta 1 for this case is n, and theta 2 will be p for the binomial distribution. And that's why I'm saying don't confuse the parameter, which we normally indicate by n for the binomial, which in this case can be denoted by theta 1. Don't confuse that with the number of trials. Remember also that the degrees of freedom now is 4 minus 1 minus the number of estimated parameters, and we only estimated the p, not the n was given. Okay, now the next slide, we have our whole test. Null hypothesis, always the known distribution, but now not specifying any value for the parameter. Against the alternative that it does not hold, there we have our alpha, our rejection region. Note that I say here reject the null hypothesis if the test statistic value is large enough. We have to be careful with this chapter because your chi-square test statistic, your chi-square critical value is determined by the number of categories, and you first have to make sure that you have that you are meeting all the assumptions. In other words, that specific assumption of all estimated expected frequencies at least 5 before you can determine your chi-square test statistic critical value. But here we have our test statistic value, and that's 3.457. Our test statistic, the critical value that we need to compare to the test statistic value, we know now that it has 2 degrees of freedom, so the critical value is 5.992, and therefore since the test statistic value is not greater than 5.992, we do not reject the null hypothesis, and we conclude that the data appear to have a binomial distribution. Now, just to emphasize the evaluation or the checking of the assumptions, I'm going to do exercise 12b as well. Now in exercise 12b, we don't work with these frequencies anymore. We work with the frequencies 15, 2, 12, and 3, which adds up to 50 families. So now, again, we want to determine whether this frequency distribution can be associated with a binomial distribution. No parameter value is given, so we have to estimate the parameter value. We estimate the parameter value by getting the grouped mean, which in this case, again, the weighted mean, where you weigh every value, number of male children, with the number of times that it occurred. So in this case, you had 15 families in which there were no male children. There were 20 families with 1 boy, 12 families with 2 boys, and 3 families with 3 boys. And on average, that meant 1.06 male children in a family. Now, still, we are busy with a binomial experiment with parameter 3 and unknown p in this case, because we're looking at families of size 3. And mu is equal to np for the binomial, so p hat in our case now is 0.353. Now we do as we did in the previous example, we substitute in there, we get our theoretical probabilities, our expected frequencies, and our cell chi-square values. But now, note, the expected frequency is not at least 5, which means we have to combine adjacent categories. So we combine number of male children instead of 2 and 3 separately, we combine them. The combined frequency will be 15. The theoretical probability will be the sum of these two. And then we can calculate our cell chi-square value. All right, so in the next table, there I've done that, and I have calculated my test statistic value at 0.407, and I'm just going to page through the steps quickly. Null and alternative, significance level, rejection region, test statistic value, critical value, and now note that k minus 1 was 2. 3 minus 1. And we have to subtract another one for estimating p. So we are left with only 1 degree of freedom in this case. And we do not reject the null hypothesis because the chi-square test statistic value is not large enough. So again, it looks like it can be a binomial distribution. Example 2 is one where we consider the Poisson distribution. In your textbooks, I will delete this and I'll motivate why later on. They say test the fit of a Poisson distribution to the data by first estimating lambda. I'm not necessarily going to tell you by first estimating lambda, and I'm definitely not going to tell you to combine or not combine. You have to know that you have to combine or not combine. But this is a genetics experiment again, and it looks at number of exchanges of chromosomes and things like that. So it's a very specialized example, but let's look at the data, the frequency distribution. How can we determine whether this the number of exchanges whether it follows a Poisson distribution? We have values, number of exchanges from 0 to 9, and the observed counts. The number of times that 0 exchanges were observed was 6. The number of times that 1 exchange was observed is 24, and so on up to 9 exchanges was observed in 2 cases. Again, lambda has a Poisson distribution has a parameter lambda that needs to be estimated, and we do that by getting the grouped mean. And again, this is 1 over n, sum of frequency weighed with the value of the random variable. So there's our mu hat. And now we can just use that in our Poisson distribution. 3.877, I'm going to round this to 3.88 for my calculations further on. I will specify clearly what you should do in the exam or in the tutorial. Okay. So let's get to our calculation table. We know now that we're working with a Poisson distribution, which means we will have to calculate the probability, our probability under the null hypothesis that we'll have to estimate is going to e to the minus lambda, lambda hat to the I minus 1 over I minus 1 factorial, where I represent the categories 1 to 10, and these categories are associated with the values of the random variable, number of exchanges, which goes from 0 to 9. 9 was the last one that was observed. But remember, the values of x for a Poisson distribution goes up to infinity. It goes up to infinity. The Poisson is defined for x 0, 1, 2, up to infinity. It's not finite like in the case of the binomial. So you always have to use in your last category 9 or more, or whatever the last category is. You have to add this or more. And then you have your observed counts. Nothing more than 9 was observed. But theoretically, there can be more. And that's why you have to indicate it as more. Now, what's the probabilities under the null hypothesis? You simply substitute your lambda hat value into each of your lambda hat value for each category, x equal to 1, and so on. Again, remember a value of I here, x equal to 0, for example, will be I equal to 1. So its probability that x is equal to 1 will be e to the minus lambda, lambda to the, this should actually be x equal to I minus 1. X equal to I minus 1. Because the first value that x assumes is 0. So sorry, this must be x equal to I minus 1. And that gives you e to the minus lambda, lambda to the I, lambda hat, of course, to the power I minus 1 to I minus 1 factorial. All right, so you plug it into that formula and you will get these values with a parameter value that I've given in the previous slide. There's your theoretical values, and now remember this. For your last category, it's going to be x greater or equal to the largest observed value. And then you get that probability by 1 minus the probability of the preceding values in the categories preceding the last category, so that you have all your probabilities adding up to 1. Because you will see this value is the theoretical value is 0.018, and you will see that this does not add. If you just calculate it for x equal to 9, you will see that your probabilities do not add up to 1. You have to consider x greater or equal to 9 for the probabilities to add up to 1. And now you get your frequencies as before. You multiply each probability by 300. Then your estimated expected frequencies add up to 300 as well. And you can get your cell chi-square values. And if you look at all the cell chi-square values, you will see that we can calculate our test statistic value here as well, because all the expected frequencies are at least 5. So all these cell chi-square values can be used just as they are. Add them up, and there's your test statistic value. And you go through your procedure, your hypothesis testing procedure. So the two things that I want to point out is, again, check here. According to your textbook, we should have combined the last two categories, but I can't see why we need to combine it, because we're working with x greater or equal to 9. And therefore, we have at least 5 in the last category. But remember that Poisson is always the last category up. It goes to infinity. So remember that. There's our procedure, null and alternative, significance level, rejection region, test statistic value, all check the assumptions, get your critical value. Note again, we estimated one parameter and we had 10 categories, so that yielded degrees of freedom 8 in the end. It's not greater than the critical value, so we can assume that it has a Poisson distribution. The last one, the last example, is again a continuous distribution. Is the sample from a normal distribution? And this is very relevant because we are making the assumption about normal distribution all the time when we do hypothesis testing. If you recall what you did in the hypothesis, all the preceding chapters, the distributions are, the distribution of your test statistic is very often dependent on assuming that your population is normally distributed. And how can we test whether a population is distributed? You draw a sample from that population and you do the following test. Now, this is a story about oxygenation rate. Again, a specialized example that you will also not understand exactly what they're talking about, but that's why the article reference was given there. What's important for us is that we have a frequency table, and we want to know whether this frequency table can be associated with a normal distribution. Are these counts from a normal distribution? Note the cell, the choices of cell it's given. We won't ask you to calculate this as they do in the textbook. We will give you the categories. These are the observed frequencies of the oxygenation rate. So what has happened is that in 12 cases, the oxygenation rate was below 0.1, and in 13 cases, the oxygenation rate was 0.25 or more. Now, again, we have to estimate the parameters. The average oxygenation rate is not known, the standard deviation is not known, but it can be calculated from the frequency table. And for the normal distribution, we're not going to ask you to calculate the standard deviation with group data, so it's given here already. X bar 0.173 and standard deviation 0.066. So now we just need to do our calculations to see whether the goodness of fit test can give us an answer. So we construct our table. Now note my rate per day. I have indicated as intervals with closed and open ends. 0 is included here, 0.1 not included, but it's included in the next, and so on. And this is rate per day. So the largest rate can be 1. So we have an upper bound there as well, and the frequencies, and they all add up to 83. So we have 5 categories. So how are we going to get our theoretical probabilities here? We know that we work with a normal distribution. So now we have to determine what's the probability that our random variable will assume a value between 0 and 0.1. Or just less than 0.1. Because 0.1, let's just go back to the wording. It's below 0.1, so you can simply say less than 0.1, and in the top category you can say more than 0.25, but because I assume in this case that we have a lower limit of 0 and an upper limit of 1, we can just simply go and calculate for the first category what's the probability that x is less than 0.1. For the second category, what's the probability that x is larger than 0.1 and smaller than 0.15. For the next ones, larger than 0.15, smaller than 0.2, and for the last one, it will be probability that x is larger than 0.25. And how do we do that? We standardize. Z, you subtract the mean, which was given, the average, you use mu hat now, and you divide by sigma hat now. And then you get a cumulative probability for standard normal distribution. So that's phi of minus 1.11, and you get 0.1335. And there's your probabilities. I think it may be best to just keep to less than 0.1 and greater than 0.25, because if you start using, I'm worried that you will look at probability x between 0 and 0.1. So let's just keep it greater than 0.25 and less than 0.1. And then you get your theoretical probabilities. You multiply by your total of 83 to get your estimated expected frequencies. You check that your totals agree. Then you get your cell chi-square values, and yes, you check that your assumptions are met. So the assumption in this case is that all the frequencies in each cell must be at least 5, the expected frequencies. and then you calculate your cell chi-square and you get your test statistic value. All right, and then you go through your process of hypothesis testing, null and alternative, significance level, rejection region, test statistic value that you calculate under the assumption that the null hypothesis is true and using normality results. Then you subtract 2 degrees of freedom in this case, because 2 parameters were estimated, namely mu and sigma. So the critical value is 5.992, and once again we do not reject the null hypothesis, so it seems that the sample comes from a normal distribution. So that is more or less a type of problems that you can get. You can have a look at a similar example, which is your homework, which is exercise 15.